Hi everyone. Today we're going to talk about integration manipulation. And really, this is just a fancy title. The main thing we're looking at is just reviewing a bunch of different integration techniques. So, part one is specifically algebraic manipulation and simplification. So let's get started. And in example one, we have root x times the quantity x squared minus 3x. Now, I went ahead and just put in a number 1 there, right, just as a reminder, right, that's to the first power. And then root x is, of course, x to the 1/2, right? So I could try to do some stuff with it, but really the simplest thing to do is just distribute, right? These are all powers of x. When we multiply, we can add the exponents together, x to the 5/2 minus 3x to the 3/2. And now this is just a simple antiderivative power rule for each of those terms. So 5/2 add 1, 7/2 divide, we get 2/7, x to the 7/2. 3/2 add 1, we get 5/2, divide by that. That's multiplying by 2/5. So 3 times 2/5 gives us minus 6/5 x to the 5/2. And of course, in the words of the immortal Mrs. Sager, don't forget your cookies plus c, right? Because this is an indefinite integral. Okay, example 2, very similar. Excuse me. So first thing, right, we have the 5th root of x squared, which we can rewrite as x to the 2/5. The bottom is 2x to the first, and what I'm going to do is I'm just going to divide all 4 of these terms by x to the first, simplify them all, and that should give me some nice functions to do the antiderivative of. So 5x cubed over 2x to the first, that's just 5/2 x squared. Negative 6x over 2x, x's cancel, we get just minus 3. Now, negative, you can imagine there's a 1 in front of this, right? Divided by 2, that's negative 1/2. X to the 2/5 divided by x to the first, we subtract the exponents, that's x to the negative 3/5. And then the last part, 3 over 2 is just 3/2. Now, nothing divided by x to the first, I could have written x to the negative first power, but I actually wanted to leave it as 1 over x, because you should know what the antiderivative of 1 over x is. That should look a lot nicer. This is supposed to be an equal sign at the end. Sorry about that. But now we have some nice things to do antiderivatives of, right? Add 1 to the exponent, we get a 3, divide by 3, so we get 5, 6x cubed. Negative 3, antiderivative, negative 3x. Negative 3/5, add 1, we get 2/5. Divide by 2/5, so we multiply by 5/2, and so 2 times the 2 in the bottom becomes a 4. And then the last part, the 3/2, and hopefully you've remembered antiderivative of 1 over x is natural log absolute value of x, and that's just times the 3/2, and of course your cookies. Okay, the next one is a different kind of simplification, right? E to the natural log of the quantity 2x cubed. Now, I'm hoping you can recognize that what we have here is a composition of 2 inverse functions, right? E to the natural log of anything, right, is going to cancel out as long as the anything is in the domain of your natural log function, which you typically don't have to worry about, excuse me, for questions like this, okay? And so, right, you can just cancel those out and we get 2x cubed. Now, in my key here, I'm noticing I forgot to do this as a definite integral. So we're just going to go ahead and adjust this along the way, right? And so my antiderivative, right, of just 2x cubed is going to be 1/2 x to the 4th, not my final answer, right? This is going to be from 1 to 3. And so we can go ahead and do that. So 1/2 3 to the 4th minus 1/2 1 to the 4th. And so 3 to the 4th is 81. So this is 81 over 2. 1 to the 4th is 1. So this is minus 1/2. So this is 80 over 2, which we know is 40. That's my final answer. Okay, but really it all starts with the beginning, right? Recognizing, right, e to the natural log of anything is going to cancel itself out, and so we get just 2x cubed. And vice versa is true, right? If this was natural log of e to the something, right, they would still cancel each other out. Okay. Okay, and now we have a couple of additional examples. You can check the key on how to do those. Okay, just some factoring and canceling stuff. Okay, all right. The next page, some more manipulation, right, is using trig identity. So a couple of trig identities you should remember. Tangent is sine over cosine. Cotangent is the reciprocal of that. And then we get the main Pythagorean identity. Cosine of theta squared plus sine of theta squared is 1. Remember, you can take this, you can divide the whole thing by sine of theta squared, for example. Or, sorry, the first one I did was dividing by cosine squared on all three of those terms. And so we get 1 plus sine over cosine. So we get tangent squared equals 1 over cosine squared is secant squared. So there's another Pythagorean identity you should remember. And then if I divide the whole thing by sine squared, cosine squared over sine squared gives us the cotangent of theta squared plus 1, and then 1 over sine of theta squared is cosecant theta squared. Okay? And now it's just a matter of, okay, utilizing these, right? And, the tricky part is knowing which one to use, right? Sometimes you can do a little bit of too much work and still get the same answer, right? But we want to try to keep it simple as always. Let's go to example 1. Okay, cosecant of theta times tangent of theta squared d theta. So looking at this, right, I don't really see an identity I can use right away, right? Tangent of theta squared, right, I could rewrite this identity, right? If I subtract the 1 over to the other side, I could substitute in secant of theta squared minus 1. However, whenever I have a reciprocal function, right, my initial instinct is always just to try to write the reciprocal first. So, for example, cosecant of theta, we know is 1 over sine theta, and tangent, I know, has a sine on top. So I have two of these tangents, right? So I'll write one of them as sine of theta over cosine theta, and the other one I'll just leave as tangent of theta, right? And now I can go ahead and cancel out, right, one pair of those sines on top and bottom. And now I have 1 over cosine, which I know is secant, tangent, and now alarm bells should be going off because this is a derivative you should know, right? This is the derivative of secant. And so my final answer is just secant of theta plus c. Okay. Now, example 2, integral of tangent of theta squared d theta. So again, right, I could plug in the substitution. Now, on this one, that's actually the correct answer. When I initially did this one, I subbed in sine of theta squared over cosine theta squared. That actually makes it more complicated, right? And so for this one, I want to use the Pythagorean identity, right? So I am going to substitute in secant of theta squared minus 1. Okay, and now, again, alarm bell should be ringing. Secant of theta squared you should recognize as the derivative of tangent of theta, right? And then the 1, think of it like if this was, dx, you would just write x, and so I just write minus theta, of course, plus c. Example 3, 1 over 1 minus cosine of z squared. So this one is already set up, right, as our Pythagorean identity rewritten, right? If I take the cosine of theta squared, subtract it to the other side, I would have just sine squared left on the left-hand side of the equal sign here. And so that's going to be my substitution. So the first step, rewrite it, 1 over sine of z squared, right? Don't forget your differential, dz. Okay. And then the 1 over sine squared, rewrite it as cosecant of z squared. And again, alarm bells should be going off, right? Because just like how secant squared, antiderivative, is tangent of theta, right? For cosecant squared, it is going to be negative cotangent. In this case, it'll be of z, not of theta. And now this is a definite integral, so plug in my values, right? So this is negative cotangent 3 pi over 4 minus minus, that's where the plus comes from, cotangent of pi over 3. And now it's everyone's favorite game, name that unit circle value. Okay, so cotangent of 3 pi over 4, well, first of all, you should know tangent of 3 pi over 4 is negative 1. Take the reciprocal, you get negative 1. Times a negative, you get positive 1. Cotangent of pi over 3, well, tangent of pi over 3 is root 3. Reciprocal root 3 over 3. Okay. There's one more additional example. You should try that, and you can take a look at it on the completed notes on Schoology. Okay. Now, let's go down to part 3. This is the part I imagine most of us are going to be struggling with, so let's talk through this. Okay. Reverse chain rule or anti-chain rule. Look for a simple composition of functions. Probably the trickiest part of this is I see that students can't recognize when we have a function inside of another function. Okay. And so that's what our focus should be, right? So on example 1, I have this integral 4x plus 3 to the third power. Now, I can tell you right now, you could FOIL this out, do the antiderivatives, combine like terms. I promise you on a multiple choice, that would not be one of the options. It would be factored, okay? And so you have to look and realize what is inside of what. Parentheses are very helpful, right? I can see 4x plus 3 here, right, is all raised to the third power, okay? And so basically what I want you to focus on is, okay, if 4x plus 3 is in the parentheses, anti-chain rule just means divide by its derivative. So the derivative of 4x plus 3 is just 4. Okay. Now, you're going to do the antiderivative of something to the third power. Well, if something is to the third power, you would use the power rule, right? And so you would add 1 to the exponent and then divide by that new exponent. And now you keep whatever is inside of there, right? And the anti-chain rule part, we divide by 4, so that gives us an extra 1/4 out there. And then my last step is just to combine these, and so I get 1/16 quantity 4x plus 3 to the fourth power. Don't forget the cookies. Okay, example 2, right? Now, fractions can be a little bit tricky, right? But remember, when you have multiple terms, right, think PEMDAS, right? Technically, you have to do 3x plus 1 first. So let me put that in parentheses, right? And now that is the composition part. All of that is inside of the reciprocal function, right? And so we kind of talked about this already. I'm going to go back up real quick to the first page, right? What is the antiderivative of the reciprocal function, right? 1 over x, natural log absolute value, right? So that's what I'm going to be using here, except the only difference here is that it's not of x, it is of 3x plus 1. That's the composition part. And so I'm going to make sure to divide by 3, but first focus on the antiderivative. So it's going to be natural log absolute value of whatever's in the denominator. And then the divide by 3 just means times a 1/3. Don't forget the plus c. Okay. Now, example 3 is very similar to example 2, but the first thing I'm going to do is I'm going to take this 5 up here, right? This 5, right, is kind of a nuisance. My first step is let me just put that outside of the integral, right? And so then I can go ahead and rewrite this. Okay, so I put the 5 on the outside. Right? Now, again, I have parentheses, right? And so the composition part should be easy to see. That's the 3x plus 1. And so I'm going to divide by 3 again. But this time, I went ahead and wrote this power of 2 as the negative second, right? Because the antiderivative here, I'm going to use power rule, right? This is not natural log for the antiderivative, right? This is just good old-fashioned power rule, okay? So power rule, add 1 to this exponent, negative 1, divide by the new exponent. So dividing by negative 1 is the same as multiplying. Keep whatever is inside of there. I took the 5 out, I divide by 3, so I tack those on, okay? And now in a multiple choice, you really wouldn't see it written like this. And so my last step was just to rewrite it to make it look a little bit nicer, right? So the 5 stays on top. This 3 is on the bottom. The negative I put in front of the fraction. I could have put it in front of the 5 as well. And then 3x plus 1 to the negative first just means it's in the denominator. Don't forget the plus c. Okay, example 4. This one looks a little bit trickier than it actually is, okay? So I'm hoping we can look at this and recognize that this looks like the derivative of one of the inverse trig functions. And so if we look back at our notes, right, we should recognize the format for this one as 1 over the square root of a squared minus x squared. So you can think of this as anti-chain rule, but you really don't need to, right? All you need to identify is what is the a, right? And so here, if this is 16, that's just 4 squared, right? And so the 4 is my a value. And so for this, I can just use the formula, sine inverse of x over a, my a is 4, plus c. Now, if this was something other than x squared, like let's say this was, parentheses 2x to the second power, then I would have to divide the whole thing by 2. Right? Then I would have to do anti-chain rule. But as it stands, right, this is one where you can just go sine inverse of x over a as long as you can identify what the a is. Okay, the next couple of additional examples, right, you can try on your own. Okay, good practice for those. All right, I'll kind of scroll past the answers there on that one. All right. And the last one, part 4, piecewise functions and integrals. We haven't really done a lot with this. This is kind of rare. It's also not particularly hard. Okay, if you have a piecewise function, I know it says f of x here. That's a typo. It should just be h of x. Okay, so one piece when x is less than 2, another piece when x is greater than or equal to 2. The question says to evaluate h of x from -1 to 4. So obviously 2 is between these limits of integration. And really all you have to do is just take the correct integral when it's greater than 2 and when it's less than 2. So I have to split this up, right? So from -1 to 2, right? Well, this is when x is less than 2. So I take the integral of the first function, dx. And from 2 to 4, so that's when x is greater than 2, I do it of the other function, right? And from here, this is just basic antiderivative stuff. I don't think this should give you any trouble, right? You can evaluate it from here. Now, some of you might be wondering, don't we have to check whether this is continuous, right? What's going on if I plug 2 into each of these functions, right? And really, it doesn't matter, right? Because, if your graph has a hole in it, so I'm going to draw a really bad sketch here for you real quick, okay? So like if I try to draw this 6x squared minus 10x, the graph actually, here, I'll circle that, okay? The graph actually looks something like this, okay? And so, even if that was an open circle, right, it doesn't change the way we do the integral, right? Because the integral is just the area under the curve. So it's like that area plus that area. And now, even though there's a hole here, right, I can still calculate that area up till that y-coordinate where the hole on the graph is, okay? So it doesn't really matter whether or not we're continuous, right, plugging that number in. The only thing you have to worry about, and this is more of a Calc BC thing, is what if your graph has like a vertical asymptote? Like if I plugged in 2 and it gave me a vertical asymptote, right? That's something you'll learn when you take Calc 2 in college or if you take Calc BC next year, okay? But yeah, for us though, right, nothing super crazy, right? So we can call it a day right there, okay? Thanks everyone, and I'll see you next time.